Hi, Calculus 1 students. We are in the continuity section, and in the class I left you with this exercise. Let's just read it together. Is there a value of a? Okay, so I hate a as a parameter, but we're stuck with it because that's how the problem has been formulated, like in the past exam, winter 2017. What I'm talking about is this a that is like inside the formula over here. It's repeated a couple of times. Is there a value of this a that makes the function, the piecewise function defined here, continuous at x equals 2? Okay, not an easy problem. It's definitely on the hard hand that you could expect in a final exam. And we will see why as we go through the problem. First of all, before I start, let me give you the usual warning. You should really attempt this problem by yourself before watching this video. It's labeled exercise, right? So if you haven't attempted the problem by yourself, close the video, have a good try at the problem, and then look at the video to see if you got it right or if you have totally no clue. Okay, with that, let's get going. So we need the definition of continuity at x equals 2. So let's first write it down. I'm going to use this space over here. So reminder, f is continuous at x equals 2. I'm just going to put a line here. So at x equals 2, if the limit as x is approaching 2 of f of x is equal f of 2. Okay? So this definition of continuity is very compact, but it does implicitly say that the limit has to exist. Okay? So you should check two conditions, one after the other. Okay? So the first condition that we will check is that it exists. And the second condition that we will check is that provided that the limit exists, it does match the f of 2. So n equals f of 2. Okay? So pretty much this will be our step 1. And this will be our step 2. Okay. So, okay, now we look at the function, and the function is has a junction point at x equals 2. So in other words, it is defined differently depending on if x is below 2 or if x is above 2. And for this reason, to see if the limit exists, we have to compute the limit from above and the limit from below. So let's label this as part of being the step 1. So since f is defined differently, depending on if x is above or below 2, we must take the limits from both sides. We must take the one-sided limits. And remember that the limit exists only if these one-sided limits match. So, and see if they match. Okay, so what I will do now is I will erase everything and I will start the calculation after erasing everything. So make sure you have this down, or if you need to refer to it, just rewind the video. It's no big deal. So now I'm erasing it. What I'm doing here is still part of step 1. So we will compute the limit as x is approaching 2 from below of f of x. Okay? And well, obviously you remember how you have done this before. So from below we mean that x is below 2. And so for that reason we take this formula. So it's the limit as x is approaching 2 from below of ax, that's it, ax squared minus 5. And from that point, fortunately, it's an easy direct substitution. That's not where the problem is hard. So what you get is 4a minus 5. As you take the limit from above, you use pretty much the same argument. In this case, x is above 2, which means you have to select this piece over here. So you have the limit as x is approaching 2 from above. And now let's copy paste this thing. X squared plus ax minus 7. Again, this is a direct substitution. So you just replace 2 everywhere there's x. So you have 4 plus 2a minus 7. Let's simplify that. 2a minus 3. Okay? Take note that the two limits actually depend on a, which is normal because a is a parameter. It doesn't depend on x. It's not relevant in the limit. It's just sitting there and ready to assume any value we would like it to have. But what we're looking for is a condition on a that would make the function continuous at x equals 2. So as I said, oh, this is not step 2, by the way. This is still step number 1. So as I said, you want the limit to exist, and for the limit to exist, the two one-sided limit must match. So in order for the limit as x is approaching 2 of f of x to exist, we need that the limit from below must match the limit from above. So the limit from below is the 4a minus 5 that you see right here. So we have that 4a minus 5 must match 2a minus 3. Now, obviously, you solve that for a. So what you get is 2a. So doing a little bit of algebra, not much. 2a is equal to 2, which means a is equal to 1. Okay, now what I'm going to do is I'm going to write that value of a right here, and I'm going to erase all the rest. Okay, so this is a candidate, by the way. We didn't finish the problem. So we have a candidate. A equals 1. Okay, now let's erase everything else. Now, in step number 2, so we know that the limit exists when a is equal to 1, but we have to ensure that the value of the limit matches the value of the function. So for a equals 1, okay, we need, well, actually, we will just say that f is continuous if the limit as x is approaching 2 of f of x is equal f of 2, okay? So what you need to do is just to find the limit, look at what it is. So the limit as x is approaching 2 of f of x. Now you could choose, we know that the limit exists for this value of a, okay? So this allows you to choose one of the two sides and take it to find the actual limit. I will choose the side from below, but it's really convenient. It's really just convenience, I mean, okay? So yeah, that's it. So this step is really because we know that the limit exists. So exists for a equals 1. So fortunately, I won't run into too much things to write underneath. And then obviously, you use the same result. So x is, we know that x will be smaller than 2. So we use this piece. And okay, now here's the difference. Now we actually plug in the value of a. So not only we take this piece over here, but whatever value that we found for a over there, which color am I going to use? Wait a minute. Oh, I'm going to use red. Perfect. So whatever value we found here, we actually replace. Okay, inside here. All right, and then we find whatever the limit is. So we have 4 minus 5, so it's negative 1. Okay? Now, f of 2, we do the same thing, right? F of 2 is labeled to be a squared. So, in other words, here I don't think there's any color that's really convenient. So, or, wait, I have purple? Oh yeah, okay, I'm gonna color this in black, which is not a worry, okay? So pretty much you use this piece. And then be careful because the value you need to replace is the value of a, right? And we found out that a is equal to 1. So f of 2 is equal to 1. So in other words, what happens is that if a is equal to 1, which is the only value for which the limit exists, the limit is going to be equal to negative 1, and the function is going to be equal to 1. Therefore, the function is not continuous at x equals 2, even for that value of a. And this is how you conclude. Okay, so limit as x is approaching 2 of f of x is not equal to f of 2. So for a equals 1. So as a result, there is no value of a, and I'm going to erase that now. It's no more a candidate. So there is no value of a that makes f continuous at 2. That's the end of the problem. Hopefully this was helpful. See you in the next video.